Hello everyone. Now as a part of our learning on reservoir simulation or reservoir modeling or well modeling, now we will learn about PVT modeling and PVT analysis, fluid characterization, and we will do that in software called PVTP. It's another product of petroleum experts. It is, I think, one of the most popular softwares that are used to perform PVT modeling. All right. Maybe you can name several other software, but at least for me, it is one of the most useful. Okay. So in this video, we will construct a PVT model, a compositional model. Okay. And we will take the material from the PVTP itself. Okay. Here, as you can see, we have several tabs: file, options, data, calculation. And let's go to the help, index, maximize, open the work examples. Here we have characterization examples and EOS. EOS is equation of state application. Okay, open the drop-down menu. Now in this video, I will talk about this example one for oil characterization, and we will cover as many sections as possible. So please note that maybe this video will be quite long, okay? But I hope it will be quite comprehensive. I hope we can learn many things together. Okay, so yeah, I will go to the PVT and then go back to the help, and then I will read the messages. So yeah, I hope you can follow and let's learn together. Okay, so this is the introduction. Example one, oil. I will read, okay? I will read it out loud and you can follow and let's learn. Okay, this guide intends to demonstrate the thinking process behind characterizing a fluid, in this case an oil with PVTP. Okay, it should be noted that this is not a guide of the essential steps for matching any fluid. This is because every fluid is different, has its own challenges, and by definition, there are multiple solutions as well as pathways to particular solution. Okay, okay, we got that. Now the scenario. An oil reservoir in the extensive Logi Mill field has been discovered. A fully integrated model is to be built to come up with a development strategy. This integrated model is to be comprised of a numerical reservoir model, well and surface network models, as well as a process model. Okay, so you have process reservoir model there, well model, surface network model, and process model. Additionally, the likelihood of flow assurance issues such as hydrate or wax formation is to be investigated, and therefore the use of an equation of state, EOS, rather than a black oil description of the reservoir fluid is required. Okay, a fluid sample was taken and analyzed in a laboratory. The engineer has been tasked with using the lab data to develop an EOS description of the reservoir fluid using PVTP, and we are the engineers. Okay, so that's for the scenario, and we go to workflow summary. It's quite long. I will not read it out loud. So let's just check workflow summary. So we have QC lab report. Okay. We will define pure components. Oh, sorry. We will QC the lab report. We will define the pure components. We will define the pseudo components. So they are different, the pure components and pseudo components. Okay. And then lab data entry, we will input the laboratory data. We will perform regression to obtain a match model. And then we will do validation, and let's check the EOS application. Okay. So from workflow summary, now we will check the data available. Data available. The following data is at the engineer's disposal. Okay, so we have this data: fluid composition, constant composition expansion or CCE experiment, differential liberation or DFLIP experiment, and separator SEP experiment. Okay, now reservoir conditions. So we have reservoir pressure, we have reservoir temperature, and the depth of the reservoir. Okay, got that. And these are the units. So we will use field units. Okay, recombined composition. Okay, so this fluid is actually a recombination fluid, and this is the recombined composition. We have nitrogen down through C20 plus. Okay, so from nitrogen to C19, they are pure components. But C20 plus, it's not C20 pure. It's C20, C21, C22, and so on and so forth. And we combine all of these heavy components starting from C20, okay, all the way to the C heaviest, I don't know what it is, C heaviest, C20, all the way through the heaviest component. We will combine them and we call them C20 plus. And this component is a pseudo component because it's not pure component, okay? And mean molecular weight of C7 plus fraction is 220 gram per mole, okay, from C7 all the way through C plus plus. Mean specific gravity, okay, 0.87. So that's the recombined composition. Now let's check the CC experiment. Okay, so we have CC experiment. In this case, we have pressure against relative volume, okay? And then we also have oil density and then oil viscosity, okay? This is the reservoir pressure and the saturation pressure is 2091. Okay, got it. Now we also have differential liberation experiment data. In this case, we have pressure, oil density, solution GOR or RS, and oil formation volume factor. And separator experiment, okay, we have this stock tank gravity, API, and then we have SEP experiment 2, separator experiment 3. Okay. Now lab report quality check. Okay. Actually, I want to read all of these messages, but given the time that I have, I will skip. If you have PVTP, you can read it yourself. Okay, because after reviewing the materials here, we will go back to PVTP and run the simulation, right? Okay. So by the way, from lab report quality check, these are the step by step. So after having this data available, now we will start, go back to the PVT, and then we will do the job. Okay, so here you can see we have file options data calculation. Okay. And then you also have this one, this one. If you open the file, you have this save and save as, and this operation. And then you can also click this one, system options. This one is actually the same with this one, options. Okay. All right, so let's go. We can start from the tab, or we can also start from this one. First, let's check the units. Let's use the default units. Click OK, and then go to option. Okay, so if you open the method, you can do either black oil, or you can also do equation of state. In this case, we will do equation of state. We will do compositional modeling. with the equation of state that we use is Peng-Robinson. Okay, stream is called, well, stream. You can input the user information, company, field, location, platform, then the analyst, and some comments here. Click OK. Okay, options and units. Now we go to data. You have select components from list, enter components. You can start from here, or you can also go, oh, this is the unit. You can also go here. Let's check. This is the equation of state component database. This is the same with this one, data, select component from list. All right, same. Okay, so let's check. So from here, we will select several components. In this case, from hydrocarbons, we have C1 down to C34. Okay, and non-hydrocarbons, we have nitrogen, CO2, hydrogen sulfate, water, and helium. And we can also create our own components or pseudo components, and they will be listed here. Okay, and some comment here. Okay, for the hydrocarbons, we will select from C1, press Control, down to the hexanes. And then for non-hydrocarbons, carbon dioxide. Okay. All right, so in the window that opens the pure components, so these are the pure components. In this case, C1 to C6 can be selected by clicking on each component, like what I showed you before. And then similarly, non-hydrocarbons, here, this one. In this case, carbon dioxide can be selected by clicking on the relevant component. Okay, finally, we can specify the number of pseudo components. In this case, here, number of pseudo components, I will use 1. Okay. All right. Number of pseudo components. Okay, so from here, we will click this one, enter composition. Okay. Let's be careful, okay? So by the way, I will show you my data. Let me check the data first. See, okay. Okay, so from here, I will stop share and then I will go to my Excel spreadsheet. Okay, here. So as you can see, I have this component. Okay. I have nitrogen, CO2 down to C7 plus. So C7 plus will be our pseudo component. I will copy this list, but yeah, I will be careful because here I have CO2 and then, yeah, let me check the number, okay, of each component in the PVTP. Okay, so here we have CO2, pure non-hydrocarbon, C1, C2. Okay, I will copy from the CO2 down to C6, like this. Just copy and paste. Okay. And then for the pseudo component, PS1 pseudo component, okay, we can type in. Okay, molar percent will be 32.1. By the way, it is in molar percent. And the molecular weight is 222. Okay, you can go back to the help and then you can see the guideline. It is 232. Okay. Okay. Please be careful. This is the list, general, number of components 10, number of pseudo 1, which is this one, PS1, which is actually C7 plus. Input as molar percent. We can also use molar fraction. Okay. And then here the reference data, reservoir temperature is 185 degrees Fahrenheit. Okay. And then the reference depth 5949, and the reservoir pressure or reference pressure is 2339. Okay. Okay, and then let me check again. 0.8, 3622. Okay. 94 for, okay. And then 226 to, I think this NC5 is 242. All right, total molar 100, 325, 32.1, remainder 0, average molar weight 92.785. Okay, so far so good. In our case, the boiling point, okay, is not reported, and we will have to be, it will it it should be estimated using the provided molecular weight and specific gravity. Okay, so from here, okay, we can check this one, exit and save. All right, you can cancel, help, view, if you want to check the units again, pseudo component properties, okay? And then binary interaction coefficients, later we will go there, and then quick calculation. If you click quick calculation, you cannot perform calculations unless there is a valid composition, including any pseudo properties which might be required. Please check your data and try again, okay? From here, we should go here, pseudo properties. Okay, let's be careful again. So we have the steps, the order, edit all, binary coefficients, quick calculation, boiling temperature. If you open the drop-down menu, you have petroleum experts, and then this one, other correlation, standing and cuts. We'll use this default setting. And then for the critical temperature, critical pressure, critical volume, and omega, we will use this one. Okay. And then this is the table for our pseudo component, PS-1, composition percent 32.1, molecular weight 232. Okay. So again, we don't have the boiling point. Okay. And it will be estimated using the provided molecular weight and the specific gravity. When you know the specific gravity as per data is 0.87. Okay, so we enter the specific gravity from the lab report, and easily we can click calculation, calculate values. Now, very easily you will get the estimated boiling temperature, okay, in Fahrenheit, and also the others, critical temperature, critical pressure, eccentric factor. All of them are calculated using this selected correlation. Okay. You can also clear boiling points if you want. Okay, number of components still 10. Number of pseudos 1. Properties automatic. You can also input manually. Okay, so with this in place, we have now reached our first milestone. Okay, this is our first milestone, which we want to preserve. Okay, why do so? Okay, wait. So this is our first milestone. We have inputted the pure components and also the pseudo component, and we also get the physical or thermodynamic properties of the pseudo component. So this is our first milestone, and we want to preserve that. Okay, so that when a characterization strategy does not yield a desired outcome, we can go back to previous milestone. Okay, so because PVT modeling is quite a long process, so it is it is important if we can save each milestone. Of course, it will be based on your preference, but best practice recommendation, you can stop here and save, and this is our first milestone. Okay, so we can exit and save, exit and save, and we can save if you want. Okay, all right. So from here, we can go to the help menu. Okay, and let's go from which one? Okay, so this is the milestone state. I think we can read it together. All right. So with the component properties defined, it is time to create the first milestone of this characterization. As briefly mentioned before, it is strongly advised that safe copies of the current state of the characterization are created whenever a milestone is reached. For example, after entering the composition and lab data, defining the pseudo properties, defining the pseudo splitting, or after performing and quality checking each regression step. These milestone copies can be created by simply saving the file under different names whenever a milestone is reached, and or a copy of the current stream can be created within PVTP. Okay, the file can be saved via File and Save As, or by pressing this icon in the taskbar. In this case, we have saved the state of the model as oil characterization. A copy of the current stream can be created via streams. Okay, so I think we can minimize this. Okay, so here we have stream. Okay, a copy of the current can be created via streams. Here streams, and then add copy import streams, or by pressing this icon in the taskbar here. In the window that opens, okay, so we have this one, add stream selection dialog, press copy existing stream, this one. So by the way, first we have only one stream, which is well stream. Now I will press copy existing stream. All right. Select the stream to be copied, which is only this one. In this case, well stream. Okay. Enter the name of the new stream. In this case, initial. New stream name, we call it initial, and provide a short description, optional. Okay. Just comment new stream, or maybe copied from well stream. Okay, press copy stream to create a copy and return to the main screen. Click this one. Now we have well stream and we have initial. Currently, we are in initial. Before continuing with the characterization, ensure that the correct stream is selected so that the save copy is not changed. Okay, we are in initial right now. Now from milestone state, we go to define pseudo component. Okay, open. All right, now I don't think I will read this, but yeah, you can open your PVTP, or you can read it yourself. Okay, so by the way, yeah, just read some sentences. Okay, now we will define the pseudo component more in more detail, more carefully. Now that we have created a safe copy of the file, we can now continue with defining the pseudo properties in detail. Previously, we entered the fluid composition and using correlation estimated the critical properties of the pseudo component from the reported molecular weight and specific gravity in the lab report. With this, the equation of state can technically be used to perform flash calculations. However, since the correlations predict generic values, the calculated fluid behavior may be quite different to what is observed in the lab, and thus the EOS cannot be used for predictive modeling. Okay, so basically, we need to do matching first. Okay, a simple test to quality check. Okay, the key is here. To quality check the current state of the EOS is to simulate one of the separator experiments performed in the lab in PVTP. Okay, the separator experiment calculator can be accessed via calculation separator, or by clicking this symbol in the taskbar. Okay, so wait a minute. Okay, so we have entered the fluid composition, and using the correlation, we estimated the critical properties of the pseudo component. Okay, so we input the molecular weight, we input the specific gravity, and we click calculate values, and then we get the general or the generic values. But maybe those values are not matched with the laboratory data. So first we will do quality check, okay? And we can do the quality check using separator experiment calculator in PVTP. Okay, so I think we can maintain this window, okay? And then we go to the calculation, okay? And find saturation or separator, or we can also use this one. Okay, let's use this one. Okay, and then read. So in the window that opens, enter the temperature and pressure of each separator stage, and then press calculate to progress to the separator experiment calculation screen. Okay, so we will input the data here. The data is actually here. Go to the data available and separator experiment. Okay, we can use this data, separator experiment 1. Okay. All right. 75, pressure 80. And the second one, 75 at 0 PSIG. And then chiller train, no chiller, streams to calculate, well stream. Okay. And then options change, equation we will use Peng-Robinson. Okay, so in this one, we can click calculate. Okay, so here we have temperature, we have pressure, gas density based on the equation of state, oil density based on the equation of state, oil density based on the SCATS, interventional tension, and then gas oil ratio. Okay. All right. So from here, we will click calculate. The calculation is complete. Okay, so by clicking the calculation, okay, it will simulate the flash through the separator stage. We do the experiment 1, the first stage, okay? So it's the flash operation with the separator. The parameter displayed can be altered by clicking on layout. So you can select which parameters you want to show, okay? And then selecting or deselecting the desired parameters. Okay, so let's check. By the way, again, you can open the help and then read the message here. Okay. So, okay, I will just talk here. Okay. So the calculated liquid density at standard conditions using the EOS, we can check here. Okay, at 0 psig. So the oil density is 890.3, and it is actually compares quite poorly with the reported liquid density. If you go back to the help, okay, and then check the separator experiment. Okay, we can check this. Wait a minute. The density, right? The density, not here. Or if you can, wait a minute. We need to check this density. We want to compare the calculated density with the density based on the lab. Okay, not here. Differential, not this one. Separator experiment. Okay, by the way, I need to rely on this. This is the thing that I mean. Okay, the calculated liquid density at standard condition using the equation of state in number 2 here. Okay, of which is this one, 890.3, compares poorly with the reported liquid density, which is 814.5. Okay, the same can be said of the calculated first stage of GOR 0.3 here, which is 761, compared to the reported GOR, which is 661. If you go back to the separator experiment, this one, the GOR is 661. Okay, so it doesn't match. So go back to here. Okay, as such, further tuning of the EOS is required to ensure that the realistic liquid phase densities are calculated. Okay, we got that. And here, the standing cuts method for calculating liquid density is known to provide accurate results near standard condition, which is this one, S cuts. Okay, standing and cuts. So provide accurate results near standard conditions, which is further underlined above. Okay, the oil density based on standing cuts is 828.8, which is closer to the reported liquid density compared to the equation of state result. Okay, so yeah, the calculated density is 828 kilogram per meter cube, is significantly closer to that reported in the lab report than the US prediction. Going forward, we should aim for the US to predict liquid densities similar to the standing cuts to ensure that the predicted density from the EOS at S is realistic or are realistic. Okay, so we want to make the result from EOS, the Peng-Robinson, as close to the standing cuts result as possible. This process has been automated in PVTP by the Automatch, which was specifically developed by the petroleum experts. Brilliant. Okay. Okay, so from here, I don't think we need to read this message. So I'm interested with the Automatch. Let's open the drop-down menu. You can see Automatch liquid density. Okay, so let's read it. Automatch liquid density. The Automatch is performed to define the pseudo component's critical properties, such that the EOS calculation of the standard condition liquid density yields similar results to another method that is known to provide accurate and reproduce the observed liquid density in the laboratory. Okay, and the accurate correlation is actually standing and cuts. It should be noted that in reality, there is a unique combination of molecular weight and specific gravity that will satisfy the density and the GOR in the experiment. Okay, so from here, I will minimize or to perform, okay, to perform auto match, we will click the auto match button, okay, which will initiate the regression. Let's find the auto match, not this one. Yeah, by the way, we are here. Just open this one if you want. Okay, EOS calculation analysis. Before we go to auto match, we can just check this. Okay, and then you can plot, you get this quality check, but still doesn't, I think it's quite match. But of course, the density doesn't match, so we need to perform further matching. Exit. We go to main. Okay, and then we will go back here, and then the pseudo component, enter composition, no. Okay, pseudo properties. Okay. Okay, by the way, we need to find the auto match. This one. Okay. Still currently we are here. Okay, now we click this one. Okay, we will press this automatic or auto match button, which will initiate the regression. Okay. The regression the regression will be terminated if the error is smaller than some tolerance or if the maximum number of iteration has been exceeded. So the maximum is currently 200. You can change. Okay, if you want, cancel. Yeah, again, it is set at 200. In this case, the automatch converts after, okay. So by clicking on like automatch, it will converge very, very quickly. Okay. So here you can check the result. You get a new critical temperature and you get a new results. Critical pressure, eccentric factor, critical volume, Coste eccentric factor, and so on and so forth. Okay. So again, you have well stream currently, and you have the initial. Currently, we are in well stream. The initial condition before auto-matching is this. And now we are after auto-matching here. Okay, so far so good. And now we will calculate this one. We will do quick calculation. Okay, to perform the separator quick calculation. Now we can click this one, but first in the well stream, we select phase envelope or this one, flash through separator stages. Okay, we will perform flash and you can change the Peng Robinson or Solver Reddick Wong. But in this case, we will press calculate. Okay. In the window, we will press this calculate button. Okay, to perform separation or separator calculation. Click OK. So you have this pressure and temperature, you have now the GOR, total GOR, oil density based on the equation of state, and oil density based on the standing and cuts correlation, oil gravity, gas gravity, and so on and so forth. Okay, now from the results, it can be seen that the EOS, this one, and standing cuts density are in agreement, quite close. 818, this one is 815.5. Okay, and for this one, at 0 psig, oil density from equation of state, it is 832, and 828 from standing and cuts. And then what about the GOR? GOR also quite match. Oh, wait a minute. Okay. The calculated first stage GOR is slightly high. Okay. If we go back to the report, the GOR is actually 661. Okay. But the result is currently quite high, 710. Okay. By the way, the error is still within 10%. So maybe it can be acceptable. Okay. Yeah, maybe for some people it is not acceptable, but arguably we can say it is quite acceptable. Okay. Now we can press exit to return to the quick calculation menu. Okay. All right. So you can see we have phase envelope. Okay. We have critical point, saturation pressure at reference condition. In this quick calculation menu, we can select phase envelope and press calculate button. All right. Okay, so this is the current, based on the current progress that we've made, is this is the phase envelope. Okay. You see the critical temperature, critical pressure, this one, Crickondon term, Crickondon bar. Okay. We are still in well stream. Okay. All right. So from here we can click this one. Okay. And then in the window that opens, we will enter the saturation pressure at the known temperature. Okay, if you go back to the help menu, so the saturation and you see the data, so the saturation condition, okay, is 185 in temperature and the pressure is okay. All right, stream, well stream, show test point on plot, of course, yes, click OK. Here. Okay, so you see the saturation condition is plotted exactly match with the phase envelope. Okay. All right. Again, the calculated saturation pressure is quite close to the reported laboratory value. Okay. Do we have zoom? No, currently. But you see roughly they match quite well, okay, between the calculated, the red line, and the data, the green cross. Okay, saturation pressure is to the left of the critical point, okay, at the left side, and thus describes the bubble point pressure. Of course, it's quite easy. So this is the critical point, okay, critical point, and yeah, critical temperature is this, and critical pressure is this, Crickondon term, 800 this line, condensate bar 2783 this line, horizontal line, and this is the saturation pressure. Okay, so again, this saturation pressure is actually bubble point pressure, because again, this is an example for oil characterization. Okay, so we will return to the pseudo prop screen. Okay, so we will click exit and then exit again. Okay, so again, this is the pseudo component screen. Okay, so again, with the above analysis completed, we will try to achieve as close match between the measured and calculated liquid phase density, as well as the GOR. By what method? By changing the molecular weight and specific gravity only. Okay, so for this following steps, for this, we will do several steps. We can change parameter. Okay, change parameter, and then we will clear boiling points here to reset the estimated boiling point. Okay, we will clear this one, and then we will press calculate values, okay, to estimate the boiling point and critical properties. All right, now it's a recalculation. Okay, so now this is the current condition, and we will press the Automatch again to ensure the calculated liquid phase density is realistic. Okay, so after clicking Automatch, now we will have these results. Okay, now we will perform quality checks, which is again the separator and phase envelope calculation to compare the calculated results with the measured results. Okay, so it's actually a cycle, so we can do it. Okay, calculated, and then flash through separator pressure, separator stages, click calculate, calculate. So this one is okay, but actually not this one. But again, you can repeat as necessary. Okay, so you can change this. That's what I mean. You can change the molecular weight a little bit. You can change the specific gravity a little bit, and then you clear boiling points and then recalculate, automatch, and do that repeatedly, okay, to finally get the satisfactory result. Okay, but of course, I don't think we will do that for now. Okay, but let me think again. Let's say change it to 225 and 0.9, let's say. You should do it maybe in try and error mode, but in this tutorial, I will just provide you with this estimation. So clear boiling points, calculate values. Now the new boiling point is here, auto match, okay? And then quick calculation, flash through separator stages, calculate. Now let's check. Okay, so density here, okay? And then GOR not close enough, but I think it's better. Okay. Oh no. Previously is 7110. Okay, 710. Now it becomes farther actually. Okay. I think at this stage we need to check this step. Okay. Yeah, so I will close here farther right. Not a good, not a good number, this one. Molecular weight and specific gravity. Okay, so let's consult the tab, the manual. Okay, this one. To ensure comparable results are achieved, please repeat the steps outlined using these new values, 230 and 0.85. Okay, as otherwise the results of all subsequent steps will be different from this guide. Okay, 230 and 0.85. Clear boiling points, calculate again, Automatch, quick calculate, calculate. Now it becomes closer. Okay, the correct laboratory value is 661. This result is quite close. And the oil density, quite close. And this one is quite close to the real value, which is 814. Okay, so with these values, a reasonable agreement between measured and calculated liquid density and also the GOR can be achieved. However, the calculated saturation pressure is a bit lower than reported. Okay, so this is okay. Exit, phase envelope, calculate. All right, this one. This is the laboratory and the calculation based on the new molecular weight and specific gravity is lower than the laboratory data. Okay, so quite unfortunate there, but yeah, this is not the end of the day. Exit. Okay, so from here, let's open again the manual. Okay. So that the future changes to the pseudo can be easily undone, save the properties in the original number store by clicking on store in the pseudo prop screen, selecting the use original pseudo props from store to this one. Ensure that when auto-matching the critical properties of the split pseudo, the same liquid density is achieved. Okay, so from here, we will click store. This option will destroy the existing pseudo archive data. View can be used to check archive contents. Do you wish to continue? No. Use original pseudo props from store. Okay, so let's be careful. Click yes. Okay, so we will this one use original pseudo props from store that ensure that when auto matching the critical properties of the split pseudo split pseudo, the same liquid density will be achieved. Okay, so go back here. So with this, we have now reached our next milestone as the EOS now reproduces the liquid density and the GOR. Although again, the saturation pressure is not very good. But anyway, as such, we would like to again retain the state of the EOS in case that we wish to revert changes made without having to start from scratch. As described before, this can be achieved via copy streams, facility, or by saving a separate copy of the file. Navigate to the main screen by press exit and save twice to create the save copies of the current stage. Okay, so we will copy and save, exit and save, exit and save. Okay. Now we will save again, right? This one, copy existing stream, and we will call it sudo props, copy stream. Okay. So this is the initial file. This is the current milestone. Now we will go back to the well stream. Okay. With the above in place, the EOS now reproduces the liquid density within about 0.2%. All right. The matching quality, and the GOR within 0.9%. So this is sufficiently close to the remainder that can be achieved via the regression by adjusting, for example, the volume shift. Okay, I'm reading this message. So the saturation pressure, however, is only around 1980 compared to the real value, which is 2091 psia in the lab report, and requires further tuning, of course. As such, the aim for the next step will be to expand the phase envelope. Okay, we will expand the phase envelope whilst maintaining the match on the liquid density and the GOR. Before introducing binary interaction coefficients, BIC, we will first attempt to expand the phase envelope and increase saturation pressure by splitting the pseudo into smaller constituent pseudo components. For this, we will first use correlations to estimate the composition profile and then lump these constituent pseudo components together into a number of pseudo components. All right, so this will be more challenging. Introducing additional pseudo components increases the granularity. It has increasing the phase envelope, as there are now components with higher critical temperatures and lower critical pressures than before. And also the degrees of freedom, giving the regression more flexibility to perform matching. Okay, this is the key, increases the granularity. Okay, so okay, we will have more freedom here. Okay, now please ensure that the original stream is selected prior to continuing with the characterization to avoid confusion and potentially breaking the milestone. Okay, so that's quite clear. Okay, so from here we will return to the pseudo props via data, enter composition, pseudo props, or by clicking this button, followed by pseudo props to enter the advanced pseudo splitting interface. During interface, we'll press advance. Okay, so data, enter composition, and then we will go to pseudo props or close, exit and save. We can also use this one, pseudo props. Okay, so now we will go to the advanced, this one. Okay, advanced button. See this with some method, advanced. All right. It's quite scary, but it's okay. It's a process of learning. Okay, to get a feel for how the shape of the composition and the number of constituent pseudo components affect the phase envelope and separator calculation, we will change one parameter at a time. Okay, and then recalculate the profile and split and perform the quality checks. Okay, here for the method. Okay, here with sun, and then mode calculate to n. Okay, now we will go back to this one. Please know for now the Automatch should not be performed as this breaks the dependency of the critical properties on the molecular weight, specific gravity and boiling point, and therefore the impact of changing one parameter might be lost in the automatching process. Okay. For further information on how the split profile and split number affect the EOS, please refer to the chapter characterization process. Okay, so here method, change one parameter at a time, change the method or change the alpha vector or split number. Okay, this one. And then we need to recalculate the profile and split. We will recalculate split and then set even split. And then perform the quality checks, quick calculation. Okay, you can do that. Okay, we can change the original, calculate, and yeah, it will be quite long process. Okay, so you see, you can change this one, you can change the alpha vector, you can change the split number, right? You can exercise yourself, but considering the long process that we need to achieve, we will consult the help menu, okay? Initially, the aim will be to try and reproduce the compositional profile from the lab report, as this will ensure that the composition is consistent, which is especially important when performing compositional tracking. However, it has to be remembered that the components do not represent any real-life counterparts, as they rather represent a group of components. And as such, it is possible to divert from the reported profile. Okay, yeah. Let's say the original profile is usually a good starting point. In our case, however, the composition is only reported up until C6, and all subsequent components are lumped into C7 plus component. Okay. This gives us relative freedom with the choice of profile that we can follow, but we should aim to have a C7 composition that is just below the reported composition of C6. Through this investigation, it can be found that with the Whitson method, it is possible to reproduce more complex profile shapes. However, in this case, the most natural seeming trend is produced using the Petroleum Expert 2 method. So if you close this one, you see Petroleum Experts. Okay, let's check, by the way. Quick calculate. Okay, so this is the current result. But of course, this current result, the phase envelope calculated is not very good. So let's check with the Petroleum Experts. Calculate, flash through separator stage, calculate. This is okay. This is okay. Exit. Now phase envelope. The same with Petroleum Experts too. So maybe we need to do further modification. Okay, so go back here. To generate the profile below, select Petroleum Experts 2 as the profile method, and then press recalculate split. Okay. Petroleum Experts 2, recalculate split, plot, composition. So it's like this. Zoom. Okay. Variables. Okay. Go back. Lab composition. And then estimated composition. Okay. Lab composition. estimated composition. So recalculate split, plot. Yeah, it's like this. Composition in mole percent versus the carbon number. Okay, just like this menu. The next, okay, next split the original pseudo into 6 constituent. So split number 6 by entering split number of 6 and then clicking set even split, this one, to calculate the split, which groups the profile into the specified number of pseudo components. And after that, press Automatch, this button, to adjust the critical properties such that the calculated liquid density is the same as that calculated with the original pseudo component only. Finally, perform the quality checks by clicking Quick Calculation. Okay, close. Now we will split number 6, set even split. Okay, so now we have this one. Okay, C7, C8, C9, C10, C11, C13. Okay, and click Automatch. Quick Calculate. And then flash through separator. Calculate, calculate. All right, still quite acceptable. Like this. Okay. And yeah, please note that this is the case. Please note that in this case, the Petroleum Experts 2 was chosen because it produced the smoothest overall profile with the data available. Okay. If the composition of higher components was known, then a different profile method such as Whitson may have been more appropriate, and in fact, with the Whitson method, a similar final match can also be obtained. It is also possible to deviate from the reported composition profile to obtain a better match. However, deviating too much may result in certain objectives, such as tracking the evolution of the C7 plus components over time cannot be met as the model composition is not representative of real life. From the separator quick calculation, it can be seen that, as expected, the calculated liquid density, this one, and the GOR, this one, have not changed significantly and are thus still close to reported values in the lab report, still quite close. Okay, but how about the saturation pressure? Okay, now it's better. Okay, so from phase envelope calculation, it can be seen that splitting the pseudo has slightly increased the saturation pressure, right? Okay, to just above the reported value of 2091. Okay, this is expected as we now have a number of heavy components with high critical temperatures and low critical pressures that tend to stretch the phase envelope. So you can expand the plot like this. Slightly higher, or sorry, slightly lower than the real data. Redraw. Okay, so this is the critical pressure. This is quite match between the laboratory data and the calculation. Okay, close. Okay, and then can exit. Can exit. Okay, So as an additional quality check, the degree of normalization applied to the split profile should be verified before accepting the pseudo split. The reason for this is that, in particular, when using the Whitson method, the calculated molecular weight and specific gravity of the constituent components may not add up to that of the original pseudo component, so that the scaling is applied when they do not. Excessive normalization is not desirable, as it can result in the natural molecular weight and specific gravity trends correlations not being maintained. Okay, to check the degree of normalization applied, the normalization first needs to be disabled. Okay, in the pseudo splitting screen, this one, press split preferences, select the no values adjusted mode for molecular weight and specific gravity normalization. Okay, let's check. Okay, Petroleum Experts 2. Wait a minute. Okay, so if you go back to the help here, actually we should be able to reach this step. But I think because of resolution issue, the current window setting cannot reach to that part. Yeah, unfortunately though, I should change the resolution, but I'm not sure when recording I can switch the switch the resolution without sacrificing the quality of the video. So instead, let's check the tutorial. So we will select no values adjusted mode for molecular weight and specific gravity normalization 203. Okay, we can do that, I think. Split preference. And then here, no values adjusted, no values adjusted. Okay, so here, no values adjusted, no values adjusted. Okay. And then press exit and save to return to the previous screen. At the bottom of the screen, it can now be seen that the entered pseudo components and the calculated totals are no longer in perfect agreement. Since in this case, the difference themselves are small, the degree of normalization is acceptable. Here, not match between the last pseudo data and calculated totals, but difference very small, the degree of normalization is acceptable. So go back, no values adjusted, no value adjusted, exit and save. Okay, I cannot go to the bottom due to resolution issue. So yeah, go back to the tutorial. To return to the pseudo props screen, please press exit and save. And now we will go to binary interaction coefficients. Exit and save, exit and save. Okay, from here. Okay, so with the chosen pseudo split, the equation of state now reproduces the reported liquid density, GOR, and the saturation pressure at reservoir conditions. Not perfectly matched, but the match is acceptable. In fact, the calculated saturation pressure actually slightly exceeds the reported, as I've just shown you, right? Such that the additional stretching of the phase envelope is not a requirement. Okay, so no further phase envelope stretching required. So with this in mind, or I should open the help binary, okay. So with this in mind, there is no direct need for the use of binary interaction coefficient. However, they could still be included, albeit small values, to provide the regression with additional flexibility. Okay, binary interaction coefficients, BICs, are a mathematical tool used to weigh the averaging of pure components alpha values. Alpha is the attractive term to obtain the fluid alpha. They do not hold a real physical meaning, but can be seen as a measure of how dissimilar interactions are between two components. Please refer to characterization process for further information on how the use of binary interaction coefficients impact the EOS behavior. Please note that large value of 4 BICs can result in severe distortion of the phase envelope. So please be careful with large values of BIC. See image below, which is for demonstration purposes only. So this is wrong phase envelope. Okay, this can happen for large value of binary coefficient. So from the pseudo props screen, we will go to binary interaction coefficients to access the menu for applying BICs. Okay, the press calculate new values button 2, which generate the BIC from the chosen correlation. Now check if the envelope is physical and note that it is now too large. Okay, should we try that? Okay, let's read it first. Now we check whether there are any BICs greater than 0.07, in particular for the pseudo components and C1. If there are, the set max value to field 4 and pressing set values can be used to change all BICs larger than the entered value to the entered value. As before, quick calculate can be used to further quality check. Viewing the phase envelope, it can be seen that the introduce of the BICs have significantly increased saturation pressure, which now exceeds the reported by 350. Okay, let's try. Close binary coefficient. Okay, so from here, we will calculate new values. All right. Please be careful here. Now, so from here, you see in C1, oh, by the way, the splitting, we should be able to do splitting. Wait, this is right. And then pseudo props. Okay, wait a minute. Calculate values, no. Calculate values. Wait a minute. Cancel. Now well stream. Go back to here. Pseudo props. Should go back to advanced. All right. So it should be here 6, right? Set even split. And then click split preference. No. No. Exit save. Automatch. Split preference. Okay. Should be split. Automatch. Okay. Split preference. No value adjusted. No value adjusted. Exit. Oh. Exit and save, right? So yeah, it should be here. Even split. So click auto match. Okay. So if I quick calculate, should be quite okay. And then exits, and then exit, and then face envelope, calculate. It's like this. Okay, so I did a mistake, I think. Recalculate split, see if it's split, auto match, and then quick calculate, calculate, calc, exit, face envelope. All right, exit, exit, exit and save. So it should be like this actually. Calculate values, quick calculation. Oh no, it's made a mistake. Oh, okay. All right. Should I go back? Should I go back here? Unfortunately, guys. If I go back here, so the props 230, this one, Automatch, sorry, calculate, Automatch. All right. Okay, so or should I go to pseudo props? This one, pseudo props, save. Okay, so I think it is good. The oil density good. All right, with close to the laboratory data, and the gas oil ratio also good. Okay, so I will be quite careful here. Exit, face envelope, calculate. Okay, not perfectly match. All right, but yeah, I think it's better. Okay, better, but okay. So click exit and save. Okay, so I think please be careful, and then from here exit and save. Okay, so now we have number 1 down to number 15. Now binary coefficient. Okay, so from here we can click new values and then quick calculation and check the phase envelope. Okay, currently like this. Okay, this is the result if we perform or if we use the new values for the binary interaction. Okay, but exit. Of course, the result can be, it can be unreasonable for this one. So we can use this set values. Okay, maximum value, this one. Now we check whether there are any binary interaction higher than 0.07. So let's check. I don't think so. No, right? No. All the numbers are lower than 0.07. But as per this one, in particular, if there are, the set max value and pressing set value can be used to change all BICs larger than the entered value to the entered value. As before, the quick calculate can be used to further quality check. Viewing the phase envelope, it can be seen that the introduction of BICs has significantly increased saturation pressure, which now exceed the reported by 350. So yes, right? So currently the calculated phase envelope is higher, or the calculated saturation pressure is higher than the laboratory data. Okay, so from here, go back here. Next, reduce the maximum binary interaction coefficient until we get a closer match with the reported saturation pressure. Please note that because the EOS already overpredict the saturation pressure without any BICs have being used, for any positive BICs, the EOS will continue to do so. All right. In our case, it was decided to progress with BICs, though not exactly required, and limiting the maximum BICs to 0.01. With this, we have now reached another milestone whose state we would like to preserve in case we wish to revert any changes made during the regression. To recreate a milestone copy of the stream and or the file as described previously, please first return to the main screen by pressing exit and save 3 times. Okay, so let's maximum value this one first. So I will exit, and I will set max value to 0.01. Okay, still set values to this one, or set value 0.01. Okay, so now it's better, right? Better. All right, very good. So now our saturation pressure based on the equation of state is matched with the laboratory data. Click exit, exit, exit and save, exit and save. Now I will, what is the name? Binary interaction or pseudo splitting. So let's call it copy exit stream. Let's call it pseudo splitting, pseudo splitting BIC. Okay, now go back to well stream. So again, we will open the manual. Now after binary interaction, we go to enter lab data. Now that we have defined the pseudo properties, split the pseudo, and have applied the BIC, we are almost in position to perform the regression to fine-tune the EOS. Before this can be done, we need to provide the laboratory data that we seek to match our EOS model against. As the lab data will form the basis for regression, it is imperative that the data is quality checked and any spurious suspicious data points are excluded or not given the same weighting as high quality data points. The interface to enter the lab data can be accessed via data, enter lab data, or by pressing this button. Okay, so this one, so I will do that. Okay, data, enter lab data. data, enter lab data. All right. Okay. Okay, so let's open the lab, enter lab data, saturation pressure. Okay, you can read it and I will input the data. Okay, so in the PSAT or saturation pressure, enter the reservoir temperature, the saturation pressure, and the temperature and the corresponding fluid density. From the lab report, these are 185, 2091, and 641 kilogram per meter cube respectively. If different units are required to enter the data, return to the main screen by pressing OK and then change the respective units via option units by pressing this one. It should be noted that obtaining accurate measurement at the bubble point, especially for near critical fluid, is difficult. Okay, again, obtaining accurate measurement at the bubble point, especially for near critical fluid, it is difficult as the liquid and vapor phase become hard to differentiate. To avoid these uncertainties, one may wish to instead regress on fluid density near rather than at PSAT. Okay, so let's input the data. Okay, now we will, for the CCE, okay, select the CCE tab and enter the relevant data for the CCE experiment. Here, the liquid density and viscosity are of particular importance for the relative volume. It is the slope of the curve rather than the absolute values that is of greater importance since it is directly linked to the fluid compressibility. Okay, so the slope of the curve rather than the absolute values. Any data we are unlikely to use in the regression, such as the relative volume of or a erroneous data, can be excluded by selecting the relevant data points and then pressing exclude. Okay, so this one, we will exclude this one. Additionally, we may wish to exclude some data point in order to speed up the regression. For example, not all points on the liquid density are required for the matching. Instead, sufficient points to recreate the profile should be used. Cells containing excluded data will be shaded gray. The process of deciding which data points to exclude can be aided by plotting the entered data as a function of pressure and temperature to identify the outlier or unphysical behavior, which can be accessed via plot. Okay, so for example, when plotting the liquid density and zooming in on the density profile above the bubble point pressure, it can be seen that the curve appears to be slightly kink near the bubble point. This one, kink. Here, see image below. This data point is best excluded to avoid the EOS fine-tune to reproduce this density profile. For the CCE, we have excluded the relative volume, the second, third, fourth, sixth, 8th, 10th, 12th, 14th entry of the liquid viscosity and every second entry of the oil density. So they will be excluded. Okay, so let's go to the CCE. So this one is quite kink. Okay. Oh, sorry. So by the way, we can, oh, it should be relative volume instead, not liquid dropout. Okay. Variables, relative volume. Okay. Plotting against pressure or temperature, relative volume, viscosity. Okay. We can right click and click exclude. So in this case, as per the guideline, we will exclude all the relative volume. Exclude. Oh, it's not exclude row actually. Okay, so oh, it's not like that, by the way. So it's not, I will include first, include row. I should like this instead, lock them, exclude. So it will be shaded gray. And then for the liquid viscosity and every second of the oil density, exclude. Okay. And this one, the second, third, fourth, sixth, seventh, eighth, 10th. Yeah, this to make the matching faster or calculation faster. 14th, exclude. So like this. Okay, so yeah. So that's for CCE. So far so good. Now we go to differential liberation. Okay, now we need to check this one. Okay, differential liberation. Please note that because the fluid composition is not constant throughout the differential liberation experiment, it is required that the same pressures and temperatures are entered as in the lab to ensure a consistent path is followed. Also, care should be taken when matching directly to the diff lab experiment, as the results are more difficult to obtain. Adjustment to the results to ensure mass balance are not uncommon. Last stage may be bled before equilibrium is established, and thermal expansion of the vessel at ambient condition can also affect the results. Select the diff tab and enter the relevant data from the diff lib experiment. Similarly to the CC experiment, the liquid density, but also the gas oil ratio and oil formation volume factor are important. Weightings can be assigned to data that is less trusted, for example, due to inherent experimental inaccuracies, the original mass balance calculation was off, or it is desired for the regression to take smaller steps. To assign weighting, select the relevant data points, select the weighting, 10 is normal, press set weighting. Data points with weightings assigned will be appear blue. Okay, now assign a weighting of 6 to all entries in the oil density column. Okay, so from here, we will go back to the PVTP and input the diff. Okay, so for diff, I have the temperature. Okay, copy and then okay, and then I will input the pressure. Okay, wait a minute. Okay, so I will make the temperature. Okay, all right. Now the gas oil ratio. Oil formation volume factor, oil density. Okay, so weighting 6, set weighting. Okay, stream again still in well stream. All right, click plot. Okay, this is for the gas oil ratio, oil formation volume factor, oil density. Okay, and then oil viscosity. No. Okay, lastly, the separator. We go to this one, SEP. Select the SEP tab to enter the relevant data for the separator experiment. Here, the GOR from the first separator stage and the liquid density at standard condition are particularly important. The reason for this being that on the first separator stage, most of the gas is evolved. It has the uncertainty in the measurement is lower, and because it is easiest to obtain an accurate oil sample at standard conditions. By the time we get to the regression stage, the EOS should already be somewhat reproducing the first stage GOR and liquid phase density at standard conditions, and thus do not require a significant tuning. Nonetheless, they are included in the regression as they act as an anchor point, which prevents the EOS from drifting too far from the former. However, we want them to have a small impact on the error function, or otherwise the regression would be too constrained and thus unable to match the other parameters. Okay, we got that. For the SEP, we have excluded the oil formation volume factor, all but the first stage GOR, the liquid density at standard conditions, and the first stage GOR have been assigned a weighting of 7 and 5, respectively. Please note that this will be discussed further in further detail as part of the regression strategy. Okay, so for first stage GOR, the liquid density at standard condition. Okay, so we will input the data. So the temperature 75 degrees Fahrenheit. Okay, and then this one 14.7. Okay, I will exclude this one. Okay, by the way, this one For the differential liberation, okay, the liquid density and the first stage GOR. Okay, so for here, I will set 5. This one, 7. And then for the differential liberation, by the way, for this differential liberation, to all entries in oil density. Okay, oil density, right? So all here, sign 6. So far so good. Now almost there. Now we will, from this enter lab data, this is the main thing, regression. The regression is the penultimate step of the characterization process, in which the EOS is fine-tuned to the laboratory experiments. The fine-tuning is performed by adjusting critical properties, volume shift, and binary interaction coefficients, such that the difference between the reported and calculated parameters are minimized. Open objective. So the objectives for the regression are to match the liquid density, to match the GOR, to match the saturation pressure, and to reproduce laboratory experiments. The overall objective for the regression state is to not only reproduce the liquid density and GOR, but also to tune the EOS such that the saturation pressure at reference conditions and the remaining data generated during the lab experiments, such as CCE, differential liberation, and separator experiment, can be reproduced. The current EOS already gives a relatively close match on the liquid density, GOR, and saturation pressure. However, the liquid density at reservoir conditions is currently not being produced and requires further refining. Okay, so this is the strategy. Okay, to strategy. To achieve the objectives above, the pseudo properties, it has the critical temperature, critical pressure, and binary interaction coefficients, and the volume shift will be adjusted to minimize the error between the lab and calculated data. However, since the regression is merely a mathematical tool, it is important to first develop a regression strategy to avoid performing conflicting regressions, like undoing already made progress, and to quality check the results after each regression step to prevent unnatural property trends being accepted. A regression strategy could be developed as follows. First, to create a list of the current objective and rank them in order of declining importance. And second, consider what pseudo properties affect each of the objectives and by how much. Like, how does objective X change by changing Y? And third, consider how changing the selected properties for the regression affect the other objectives. And the fourth, consider which parameters would be more difficult to readjust at a later stage and thus decide on a suitable anchor point. However, before we start considering the above, we should take a moment to gain an overview of how well the current state of EOS reproduces the lab experiments, taking the lab experiments in turn. Okay, so let's do the regression. First with the CCE. The CCE experiment calculation can be assessed via calculation, constant composition expansion, or by pressing this tool in the taskbar. In the window that opens, specify the temperature and pressure range over which the simulation is to be performed, and press calculate to progress CCE calculation screen. Okay, let's dig in. Okay. All right, now maybe I will save. I will call it before regression. Okay, now let's do the regression. Calculation, constant composition expansion. Okay, well stream. Okay, we will set this temperature to be 185. The same temperature, pressure from 200 to 400. Number of values, 1, this to be 200. And then calculate. Calculate. Voila. Calculation is completed. And then, all right. Okay. So for the CCE, we are only interested in the oil density. This one is liquid dropout. I want the oil density. Okay. I want the viscosity. Okay. So this is the current condition. Density. I should go back to my, okay, cancel, cancel. I need to check the data, enter lab data, CCE, what happened? Oil, I have the oil density. I have the oil density data. Okay, so again, okay, calculation. Wait, calculation. Okay, so this what happened. Okay, so actually they don't match. This is for the oil density and also for the oil viscosity. Okay, if additional data such as GOR had been provided in the lab report, then the same separator train as used in the experiment would need to be specified. This is because the GOR is path dependent, and thus using a different separator train would result in different GOR to be calculated. Okay, in the window that opens, after pressing calculate, and then we wait until the simulation is completed. When the simulation is completed, we show the plot, and yeah, we can see that the current prediction and the data don't match. All right, so far so good. So it is what it is. Again, if you want to check the analysis. Okay. So from here, we can click main and then calculation. Okay, we differential liberation. Okay, again here we input the temperature of 185. The stream is well stream. Now for the differential liberation, I provide the data. This one, or it is in PSIG, so should be this. Okay, again, calculate. So for this one, let's see, plot oil density first. I want to check. Okay, not really match. Okay. Above saturation pressure, the CCE and differential liberation provide equivalent results as the composition is constant since no gas is evolved that could be removed from the cells. Okay, as such, as we already observed in the CC experiment, whilst the EOS reproduces the general trend, it generally overestimates. Okay, although the trend is good, but overall it overestimates. Gas oil ratio. In my case, not really match. Okay. What about the oil formation volume factor? Sorry, redraw. Yeah, this is the current condition. The calculated GOR not relatively close. Okay, and exit. And then go back to the main. Now the separator experiment can be accessed via calculation in the taskbar and then separator. Okay, in the windows that opens, specify the pressure and temperature of the differential separator stage, which should have been saved from the first time we assess separator experiment after defining the pseudo properties. That's why we have this one. Press calculate and then calculate. Calculation is complete. Okay. Now, as we can see, this gas oil ratio this one 668 and then this one 816. Okay, the calculated liquid density, which is 816 kilogram per meter cube, compares well with the reported value, which is 814.5 kilogram per meter cube, and the calculated GOR, which is 668, also compares well to the reported value, which is 661. Okay, so let's go back to this one. So if you read the manual, you can see that at this point, they don't match. So at least we get the process right. At least we know the process until now. Gas oil ratio match quite well. I don't know what happened in my case. Maybe I can do better. Some modification. Oil formation volume factor, not really good. So here, in summary, the OS currently provides an adequate description of most of the fluid properties. It has the liquid density and GOR from the separator experiment, the liquid density and viscosity above saturation from the CCE, and also the GOR and oil formation volume factor from the differential liberation experiment. However, a current shortcoming is the EOS inability to produce the measured densities below saturation from the differential liberation experiment. Can now take a moment to consider these outcomes and steps above to develop a possible regression strategy. Okay, an example of development of possible regression strategy for this fluid can be seen. Yeah, so at the end of the day, we need to work alone without the results provided by the manual. But given the time that we have, I will not do further. But if you are interested, you can read this example, read this guideline. Like for this one, create a list of the current objectives and rank them in order of declining importance. Like this, consider what pseudo properties affect each of the objectives and by how much. Like this, consider how changing the selected properties for the regression affect the other objectives, and consider which parameters would be more difficult to readjust at a later stage and thus decide on a suitable anchor point. Okay, so if you're interested, you can read this message. But we still have best practice like this one. If you open the drop-down menu, you can read this guideline, the best practice, primary regression. This is for the quality check. And then validation. Okay. And then this is the regression summary. What to do next. By the way, let's check the viscosity regression. Okay, so I think we can stop it right now, and hopefully we can cover the regression at the next opportunity. So clearly we still have many things to learn. Okay, so at least we have done so far. And then this one, copy existing stream, call it matching first trial. Okay, so we have inputted the oil, the composition, and then we input the laboratory data, the separator experiment, differential liberation, constant composition expansion. All right. And then we try to match, we generate the phase envelope, we try to match the liquid density, and then viscosity, and then the gas oil ratio. And we have done so far, but currently at this state, at this condition, we still haven't got a satisfactory match. So in the next opportunity, maybe we can modify a little bit and then do further regression to obtain better match. Okay, so I think we can call it a day. Thank you so much for watching and see you again in the next PVTP videos. Thank you.